5.9 logarithmic functions. I'm missing the 5.9, but I believe that's right. So a logarithmic is basically a question. It provides the answer to the following question. What exponent do I need to have with this base to equal a known value? So let's look through an example. So let's say I have the log, that's the abbreviation for logarithmic, the log 4 of 16 equals what? Okay, so 16 is the known value, right? So this value here, 16, this is the known value. Okay, 4 is the base, and the answer, the question mark, that's the exponent that we're looking for. So we really are trying to figure out this one. 4 to what exponent is 16? Well, I know that 4 squared is 16, right? So that means that the log base 4 of 16 is equal to 2. It's very similar to square roots to me. So for example, the square root of, let's use the square root of 81. The square root of 81 is a question. It's asking you, and the square root has an index of 2, it's asking you to figure out the value that you need here so that when you square it, you get 81. So this answer must be 9. Well, technically plus or minus 9, but we've defined this to be the positive only. So, alright. One of the reasons that we have logarithms is to help with inverses of exponentials. And so let's find the inverse to this and see if you can figure out what I mean with that. So y equals 2 to the x. We're going to find the inverse. That means that x is equal to 2 to the y. And now I need to solve this for y, and I don't know how to do this. Okay, except a log allows you to do this. So taking a log with this base, so a log base 2, so we're going to take a log base 2 on both sides, is going to allow me to find out what y is. So if I take the log 2 of x, and I take the log 2 of 2 to the power of y, so the whole thing, then that should figure out what y is. So by definition, this gives you y. So that's it. So the inverse of y to the is equal to 2 to the power of x is y equals the log base 2 of x. And that is the definition of a logarithmic function. Okay, notice here's the definition. The logarithmic function is the base e where a is larger than 0. So we'll talk about some of this a little bit in a second. A cannot equal 1 is denoted by y equals log a of x. And it's defined as, or it's defined by, so here's the definition, and notice that it says if and only if x is equal to a to the power of y. So here they went backwards. They said that this x with that exponent needs to be worth y to create the exponential function that goes with it. Alright, so why does a have to be larger than 0? Well, this a has to be larger than 0 because for that to be an exponential base, remember exponential functions, so for example a to the x, we said that this a had to be larger than 0. Right? Otherwise, if it's negative, sometimes we get y values that are positive and sometimes negative, so they zigzag. A cannot equal 1 because 1 to the power of x is always just equal to 1, so then we don't have an exponential function. So these definitions here are part of, these conditions here are part of the definitions that we worked with exponential functions. So the logarithmic function is going to be tied to an exponential expression or function. Okay. So let's look at a couple of things here. So if 4 squared is 16 and 4 is the base, then the log base 4 of 16 is 2. If 2 to the 5th is 32, then the log base 2 of 32 is 5. So these are your exponents, right? Those are the exponents. So logarithmics give you exponents, okay? So 10 to the 7th is 10 million, then the log base 10 of 10 million must be 7. And this is an important exercise, so rewriting these in the equivalent logarithmic expression, or vice versa, is something you should be able to do. So if 3 to the 4th is 81, then the log base 3 of 81 has to equal 4. And if 7 to the negative third is 1 over 343, then the log base 7, because the base is 7, of 1 over 343 is a negative 3. So notice you can get positives and negatives out of logs. Okay? Alright, so let's look at the domain and the range of exponential functions, and then we can talk about logarithmic functions. Because keep in mind, in inverse functions, the second part, we said that the domain and range of the original, so this is going to be the original function, can be used to find the domain and range of the inverse. So exponential functions, again, let's look at one just to refresh ourselves, specifically 2 to the power of x. So the domain was, for exponential functions, is all real numbers, right? You can plug in any x you want. 2 can be raised to any exponent. The range, well, keep in mind the exponential function has a horizontal asymptote, right? So it looks like this. So the range would be from 0 to infinity, not including 0, okay? Not including 0. Okay. So if the logarithmic function is the inverse, then the domain and range for the logarithmic will be, well, you can just swap those, right? Then we say we can swap x's and y's. So the domain for the logarithmic is the range of the inverse. So the domain of the logarithmic has to be larger than 0. And we already talked about that a little bit here, right? Sorry, that was the base. Where is it? Sorry, here. I think I skipped it sort of on purpose, but you know, it was mentioned here. And then the range for the logarithmic would be the domain of the original. So the logarithmic has a range that goes from negative to positive infinity or all real numbers. Okay, let's do a little more practice in rewriting. So changing an exponential to the logarithmic equivalent. So how do you do this? Well, keep in mind that this is the base you're looking for, right? So the log base 5 of t is equal to 8, because I did say a while back that logarithmics, okay, those are exponents, so the answer must be an exponent. So the exponent is the answer. Okay, so here the log base x of 12 is a negative 2. And here we would say the log base e, and we'll talk about e in just a second, of 10 is equal to x. Right, I meant in a second or a little bit. I think I'm going to save that for another lecture. So, but e is it's called the natural base, and we might do an activity for that, or I might just show it sort of to you where it comes from and save that activity to pre-calc. But the natural base is what we denote with e. So you should also be able to go the other way around. Change the logarithmic expression to equivalent expression involving an exponent. So there's your base. So I'm looking for a base 2. That's the exponent, so that goes over here. So 2 to the y is equal to 21. Okay, that's a z there. So the base of z to the exponent of 6 is supposed to be 12. Or the base of 2 with an exponent of a is equal to 10. And so you should be able to rewrite it in either direction. Okay, so you should be able to go from an exponential to a log, or from a log to an exponential. Occasionally, you can rewrite and find an exact value for this. So, so right now, if I ask you what is the log 3 of 81, maybe some of you are doing this in your head already, you know what the answer is. So, but we can add an exponent or a variable here. We can just say that, well, that's x, right? Then we can say, well, if this equation is true, then 3 to the power of x is equal to 81. And then to solve this, 81 better be a base 3, right? Because we did exponential equations a long time ago. And 3 squared is 9, and so you need 2 of those. So you actually need a 3 to the 4th. So x must be equal to 4. Right? Same thing over here. Let's just put an exponent or a variable there. So that means 2 to the power of x is equal to 1 over 8. So somehow 1 over 8 has something to do with 2. Now some of you know these well enough, and others you may have to look at 8 and see, well, how does that break down? So 8 divided by 2 is 4 divided by 2 is 2. So this is a 1 over 2 cubed. Keep in mind that if you have an exponent in a fraction, you can rewrite it and just change the exponents to a negative. So now you have the same base 2 here and here, so that means that x is a negative 3. Okay, last one, it's a little more difficult. Okay, so it says this base, the square root of 3, to the exponent of x, and that is supposed to equal 81, right? Okay, there is more than one way to do this. So what I'm going to do is use a different notation of square roots. So a square root is a second root of something, right? And if you don't have an exponent here, you can put a 1 there. So instead of writing an x, let's just write that with a 3 and see what happens. So this is the second root of 3 to the first. How can I rewrite that? Well, a long time ago we did fractional exponents. So this 1 becomes the top of the fraction, and then you divide by 2. So you can write this as a 3 to the power of a half. And 81 we saw as a 3 to the power of 4. We saw that over here. Okay, then you do a half times x, which is a half x, because exponents on top of each other multiply. So you get 3 to the 4th. And then you finally have an equation you can solve. So a half x is 4. That means x must be 8. And that's your answer. Okay? I believe that's it. Thanks.